In this part of the video, I'm going to talk about using f-tests to compare linear regression models, and I'm working with this part of the regressiondemos.r code file. So here we are in R, and for the sake of the example, I'm going to fit a model called mod_battery color, which is a regression model that has battery and color predicting price. And I'm just showing the summary table of this regression model right now in order to ground us before we do the model comparison. I'm not going to interpret each of the slopes, but the point is that it has battery as one of its predictors, and it has 3 indicator variables representing the color variable also included. And I'm going to fit another model that's just called mod_battery. This is the same as one that we already used as an example earlier in this session. And price is the response variable, and there's only one predictor, battery. So the only difference between these two models is that this one includes the color variable as a predictor, and this one does not include the color variable as a predictor. So now that I have these two models stored as objects in my R environment, I can call the ANOVA function on them, ANOVA. This function, in the use case that I'm going to recommend to you, takes 2 arguments. Each of them is a model object. For example, a model fit by ln. So this first argument is mod_battery, the simpler of the 2 models, the one that just has battery as a predictor. And the second argument is mod_battery color, which we defined up here. And it's exactly the same model except with one additional predictor, color. It's important that these models be nested, so one of them should be the same as the other, but with additional predictors. And this function allows us to compare the fit of these 2 models. We get a brief summary table of an f-test. We have an f-statistic of 10.23 with 3 and 495 degrees of freedom, and the p-value is low enough that this result is statistically significant, indicating that mod_battery color explains significantly more variance in price than mod_battery. A more complex model will always explain more variance, but not necessarily significantly more variance, and that's what this test is getting at. The model with battery and color explains additional variance that was part of the residuals, part of the error variance in the model that only had battery. So this f-test compares the extra variance explained by the more complex model to the error variance from the more complex model, which is the variance that remains totally unexplained across this whole scenario. A ratio of 2 observed variances from the same theoretical distribution has an F distribution, and this p-value comes from calculating how extreme this F ratio, this ratio of variances, would be relative to what would be expected due to chance alone in a world where they are drawn from the same distribution. In other words, where the variances represent the same population variance. Long story short, this tests whether the extra variance explained is enough that it would be unlikely to happen due to chance by adding purely random variables to the model. So adding color on top of battery is better than adding purely random variables to the model. This f-test has 3 numerator degrees of freedom and 495 denominator degrees of freedom. So we would write the result of this f-test in a paper in APA format by using the letter F, and then in parentheses we list both degrees of freedom, the 3 and then the 495, the F ratio itself, and specify that the p-value is less than 0.001. The 3 numerator degrees of freedom here corresponds to the 3 extra parameters that were estimated in the more complex model. Adding color required adding 3 indicator variables. The color factor has 3 degrees of freedom. Color as a whole, with its 3 degrees of freedom, significantly improved the model fit, that is, significantly reduced the error variance, or the sum of squared residuals. Let's try another example. Here I'm going to fit a model that I'm calling features, mod_features. This mod_ thing is not required to name models, by the way. I'm just using it in this example so that I have a consistent naming convention throughout this demonstration. But anyway, this model is called mod features, and it uses all 5 features of the robots to predict their price. So it's a linear combination of transport, material, color, mass, and battery. Then I'm going to fit an even more complex model. This one's called mod features ratings, and this one has the same 5 features: transport, material, color, mass, and battery, and the 3 subjective ratings, fun, practical, and cool, all predicting the price variable. I can do an f-test providing a model comparison between these two models as well. This f-test also has 3 degrees of freedom, in this case because I added 3 variables, each of which had 1 degree of freedom representing it because they're just continuous variables with a single slope each. And this summary table tells us that the model that includes the 3 subjective ratings explains significantly more variance in the price than the model that only has the 5 objective properties of the robots. This is an F of 21.12 with 3 and 489 degrees of freedom. The 489 comes from the more complex model, so it's the result of our sample size minus the number of parameters estimated in the more complex model. And the p-value is low enough that we would definitely argue that this is statistically significant. Adding the subjective ratings improves the model fit by more than would be expected due to chance alone. And we could write this f-test like this. Another case where f-tests comes up in statistics classes is to provide a table summarizing all the main effects of the variables in the model, adjusting for one another. This kind of table is commonly called an ANOVA table. The ANOVA function does not provide this kind of table. I'm emphasizing this because students often are very confused about what this function does. You can run this ANOVA function that we used up here for models comparison. You can run it with one argument, one model argument, and you will get a table that looks like it could be a regular ANOVA table, this thing that we refer to as an ANOVA table that summarizes all the main effects of the variable in the model, adjusting for one another. But the result of calling this ANOVA function with a single model argument does not provide a real conventional ANOVA table. So be careful about it. I recommend only using this function to compare 2 models at a time, like we've done here, and never using it on a single model object, because the result that it gives you with a single model object, while it is a consistent statistical thing, it's not a useful statistical thing most of the time. If you want a regular ANOVA table, you can try this function. It's called ANOVA with a capital A, and it's in the CAR package, and I will talk more about that in a couple of weeks. For more information, you can see this URL while you're at it, and this URL is in the code file. This is an actual comment in the code file, so you can get it from there. In 2 weeks, I'm going to revisit this topic and cover in more detail how to make a regular ANOVA table, so you don't need to visit that URL right now. We will come back to this, but I just want to give you this warning so that you're not, in the meantime, running this function with a single model argument and thinking that it gives you a summary of all the main effects adjusting for one another.